So first I drew a diagram, and you have the y-axis, the x-axis, and the z, and the sheet is going from negative infinity to positive infinity in the y-axis, and it's going from negative L over 2 to L over 2 in the x-axis. I also chose a field point P on the z-axis as just a reference point, and I took a slice of the sheet dx and dy, which would make a square, so the area would just be dx dy. And you take delta q, which would be the charge in this small square, as equal to q over q, as in the total charge of the whole sheet, over the area, dx dy. And we do this because we already know how to find the electric field at delta q, which would just be E equals k delta q over r squared. So next I drew another diagram to find r. So I have the y, the x, and the z. And I know there's the point P and my delta q over here. And I know that this connecting line would be r, which forms a right triangle with this leg and this leg. So I know that this leg is actually just the hypotenuse of the point Q on the y-x plane. So that would just be the square root of x squared plus y squared. And the other leg is just z. So to find the hypotenuse of that, you have to take the square root of z squared plus the square root of x squared plus y squared, all squared. So I replaced r with that, and then simplified, that just becomes z squared plus x squared plus y squared. So then I know that I also have to take the sine theta of the equation because you were in the z direction. So you have to use this as theta, and then sine theta would just be z over the hypotenuse, so the square root of z squared plus x squared plus y squared. So I substitute that into the equation, and I get this. And multiplied together, it just becomes z squared plus x squared plus y squared to the 3/2. And it becomes the 3/2 because this is stuff raised to the first power, and this is stuff raised to the 1/2. So multiplied together, it becomes stuff to the 3/2. So now I can substitute delta q for the entire sheet, which is just what we found before. So delta q is equal to q over a dx dy, and I just plug that into the equation. And I know that q over a is just equal to eta, so I substituted those in and pulled dx dy to the outside of the equation. And the dx dy tells me that I have to do a double integral, so I have to integrate from the y and the x. So the integral from the y would just be from negative infinity to infinity, and in the x it would be negative L over 2 to L over 2. So I plugged that into Wolfram, and they gave me this equation. And I know that you can pull out the 2k eta times z because those are just constants. And I know that k is equal to 1 over pi 4 pi epsilon naught. So the 4's will cancel out, and that just leaves me with eta over pi epsilon naught. So using this equation, I can find out what the expected behavior would be if z was much less than L and if z was much greater than L. So if z was much less than L, that would mean that you're dividing by a number that's approaching 0, which would cause the whole thing to go to 0, to go to infinity. So then as the inverse tan goes to infinity, the whole thing just approaches pi over 2. So that plugged into the equation would give me the electric field is equal to eta over pi epsilon naught times pi over 2. And that's just the equation of an infinite plane, which makes sense because as z gets very close to the sheet, it looks like an infinite plane. And then if z was much greater than L, you're dividing by a really large number, which causes the whole thing to just approach 0. And taking the inverse tangent of that will just cause the whole thing to just approach itself, which would make the equation L over 2z. So you plug that in, and it becomes the equation of an infinite line, which makes sense because if z gets really far away, the reference point just looks like a line of charge.